This is day 19 of Advent of Cyber 2024, and this challenge is called I merely noticed that you're improperly stored my dear secret. Glitch was keen on uncovering Mayor Mauer's deeds. Today he was sure he would find something neat. He knew the mayor had an office downtown, where he kept his dirty laundry, the big old clown. He approached the site silently, not knowing the door was closed so untimely. At the front of the door, a smart lock awaited. Glitch smiled cause he knew it could be subverted. But oh, big surprise, the lock was eerie, a game controlled it, Glitch almost teary. If you're wondering how this came to be, Mayor Mauer himself will explain it quickly. Technology gets broken every day, was his claim, but nobody knows how to hack a game. Will Glitch be able to pass through the door, or will he end up with 0 as a score? So the learning objectives are understand how to interact with an executables API, intercept and modify internal APIs using Frida, and hack a game with the help of Frida. So even while penetration testing is becoming increasingly popular, game hacking only makes up a small portion of the large cybersecurity field. With its 2023 revenues reaching approximately 180 billion, the game industry can easily attract attackers. They can do various malicious activities, such as providing illegitimate ways to activate a game, providing bots to automate game actions, or misuse the game logic to simplify it. Therefore, hacking a game can be pretty complex since it requires different skills, including memory management, reverse engineering, and networking knowledge if the game runs online. The executable file of an application is generally understood as a standalone binary file containing the compiled code we want to run. While some applications contain all the code they need to run in their executables, many applications usually rely on external code in library files with the SO extension. Library files are collections of functions that many applications can reuse. Unlike applications, they can't be directly executed as they serve no purpose by themselves. For a library function to be run, an executable will need to call it. The main idea behind libraries is to pack commonly used functions so developers don't need to re-implement them for every new application they develop. For example, imagine you are developing a game that requires adding two numbers together. Since mathematical functions are so commonly used, you could implement a library called libmaths to handle all your math functions, one of which could be add. The function would take two arguments, x and y, and return the sum of both of them. Note that the application trusts the library to perform the requested operation correctly. From an attacker standpoint, if we could somehow intercept the function calls from the executable to the library, we could alter the argument sent or the return value. This would allow us to force the application to behave in strange ways. Frida is a powerful instrumentation tool that allows us to analyze, modify, and interact with running applications. How does it do that? Frida creates a thread in the target process. That thread will execute some bootstrap code that allows the interaction. This interaction, known as the agent, permits the injection of JavaScript code, controlling the application's behavior in real time. One of the most crucial functionalities of Frida is the interceptor. This functionality lets us alter internal functions, input or output, or observe their behavior. In the example above, Frida would allow us to intercept and change the values of x and y that the library would receive on the fly. It would also allow us to change the return sum result that is sent to the executable. So let's take a look at a hypothetical example. So with this one, it prints out a number. And what if we wanted to replace the value with, let's say, 1337? So before proceeding, we will run free.trace for the first time so it creates handlers for each library function used by the game. By editing the handlers, we can tell Frida what to do with the intercepted values of a function call. To have Frida create the handler files, you would run the following command. Frida.trace on the file -i and assume everything. You will now see the handlers directory containing JavaScript files for each function your application calls from a library. One such function will be called sayHello and have a corresponding handler at handlers libshello.so sayhello.js, allowing us to interact with the target application in real time. We don't need to understand what the file does just yet. We will review this later in the task. Each handler will have two functions known as hooks, since they are hooked into the function respectively before and after the function call. On enter from this function, we are mainly interested in the args variable, an array of pointers to the parameters used by our target function. A pointer is just an address to a value. On leave, here we are interested in the retval variable, which will contain a pointer to the variable returned. So interceptor.attach, and you're passing it module.getExport by name, say hello, and on enter function logarg state, on leave function log retval state. So we have pointers and not just variables, because if we change any value, it has to be permanent, otherwise we'll modify a copy of the value, which will not be persistent. Returning to our objective, we want to set the parameter with 1337. To do so, we must replace the first arguments of the args array, arg0, with a pointer to a variable containing 1337. Frida has a function called pointer that does exactly what we need. Allocate some space for a variable and return its pointer. We also want to log the value of the original argument, and we have to use the function toInt32, which reads the value of the pointer. So we've got the onEnter function. We are retrieving the original argument. We are logging the original argument. Now we're changing the argument to 1337. When we rerun the executable with Frida, we notice that we can intercept the program's logic, setting 1337 as the parameter function. The original value is logged as expected using the following command. So I ran hello 1337, and we can see original argument and all the other information. Now that we better understand Frida's capabilities, we can return to Frida trace. We have already seen that it generates the JavaScript script to hook a specific function automatically, but how does it know which function needs to be hooked? The parameter -I tells which library to hook, and I can filter using the wildcard tracing all the functions in all the libraries loaded. So for this challenge, we just need to do start machine, and it will open up in split mode like this. Okay, so it's now loaded. What we need to do is go into the terminal, and we need to go to our desktop. So just cd desktop try unlock me, and then we need to run try unlock me, and that has brought up the game. So space to continue, so we can use the arrow keys to move around, and then space to interact and talk. So welcome to try unlock me 3.12, the only game-based lock in the world. A game Aunt Smart looks good enough. The mayor fears any lock that's smarter than him. I don't know how it works. So to open this door, you'll need to prove you are mayor Mauer via our patent-pending 3-factor authentication system. So the first factor is that random number thingy the mayor has, one-time password, and we don't have that. So we now need to terminate this game instant and execute Frida to intercept all the functions in the libaocgames.so library. So we will do frida-trace.try unlock me -I libaocgame.so. Okay, so now we should open another terminal, and we'll go to the desktop, try unlock me again, and there's handlers in there now. So we'll go handlers, and then libaocgame, and then we'll open up Visual Studio Code within here. So within here, we should select this first one, and you should be able to select, yeah, that's the first one, Z7 set, and JavaScript file with hook defined. The I at the end of the set OTP function indicates that an integer will be passed as a parameter. It will likely set the OTP by passing it as a first argument. To get the parameter value, you can use the log function specifying the first element of the array args on the onEnter function. So if we first shrink this, we can then add log parameter and add the args, the first argument, and convert to int32. So if we go to the game here, we move around to this guy, spam space to get to the thing again, and we can, let's say, just enter the same number that they did. Let's take a look at the terminal. It should have outputted it. So there's 517833. Oh, okay, I misunderstood that. So when the game loaded, that's the value that it gave it. I thought when we entered ours it would show something here, but no, we should have gone to here and entered that exact number. So 969145. So 969145. We've done that. We've got a flag here, so we may as well put that in now. So THM1 tough password. So that's the first question answered. So now back to here. Explore the new stage. You'll find another penguin with a costly item named right price. So we're walking all the way to the right here, and there's the penguin. So we are verified to be at least 1/3 of mayor malware. So second authentication. So we're meant to buy the flag 2 there with money, but we've only got 1 coin. So if we go back to VS Code, we should find this one here, validate purchase, and let's take a look at the prices for each of them. So okay, I think we're meant to actually try buy one of them, or is it entering the store we first need to do? If we go to here, is it showing in the console now? Yes, it is. So I've got this, this, and this. So by a simple inspection, we can determine that the first parameter is the item ID, the second is the price, and the third is the player's coins. If you manipulate the price and set it as 0, you can buy any item you want. So if we go to here, VS Code, and change this so args1 is equal to pointer 0. with that, we should be able to go back. We'll exit the store and then reopen it. And it seems like the game may have crashed. Okay, so let's try this all again. Okay, so 560346. Now I need to go all the way back and talk to the penguin again. Okay, so now with the shop open, I should hopefully be able to buy flag number 2. Yes, we did. And we're now very negative. But let's enter this flag in. THM credit card undeclined. So we have that one now. Now we need to go all the way to the right for the third and final one. So there's this penguin right here. So with this one, we need to go back to VS Code. Select the biometrics one, and we will take a look at the parameter and paste that into here. So if we were to run it, we'd see something like this. The output does not seem very helpful. You may have to consider another way. You can log the return value of the function by adding the following log instruction in the onLeave function. So we could just copy that, paste that in, and we're specifying what we're returning. So the value returned would be 0, which may indicate that it is a boolean flag set to false, which value will set it to true. Can you trick the game into thinking the biometrics check worked? So yep, changing it to 1 would make it true. So if we do that, so instead of it being false, so when we go back and we try it, doesn't matter what value we put in, we've changed it to be true. Although we need to go through all this, and we need to go back. Maybe it's, let's take a look at the terminal. So it's doing that check a bunch, but it's not logging the onLeave. Would help if I actually saved. There we go. Now we go back. So we have now tricked them into thinking we are malware. We have a third flag, don't smash your keyboard, and that is all the questions answered. So if you like this video, make sure to like and subscribe.